All right. Excuse me. Guys, obviously I'm away today. You've got an upgrade yet again. But I do want to do a quick lesson today on something related to what we've been talking about. And it's called tree diagrams. And a tree diagram is just a way of visualizing some theoretical probabilities. So it's a way to kind of put something on the paper that you can actually look at. And it can help us figure out what all the possible outcomes are in scenarios that are a bit more complicated. Maybe scenarios where we do something more than once or where we do different activities. So let's take a look at an example. Possible outcomes. If first you roll a die, it says a dice, but that is plural. It should really say roll a die. But anyway, so we have, our dice here, and we're going to roll them. And then after that, we're going to take a coin and flip it. And then after that, we're going to take a coin and flip it again. And the question is, how could this possibly work? How could it go down? Well, when we roll the dice, the die, our possibilities are getting a 1, or we could get a 2, or a 3, or a 4, or a 5, or a 6. All right, so those are the possible outcomes there. And then what we want to do in a tree diagram is from here we would say, okay, if I rolled a 1 on the die, what happens when I flip the coin? Well, there's two possibilities. I can either flip the coin and it will come up heads, or I can flip the coin and it will come up tails. I don't know why I put that so high up, but that's okay. So I could roll a 1 and then flip heads, or I could roll a 1 and then flip a coin that comes up tails. So I am going to redraw that because it's going to make me crazy when I go to actually do this. I'm going to move this up. There we go. Heads or tails. And obviously for the 2 as well, it could come up heads or it could come up tails. And for the 3, it could come up heads or it could come up tails. And the 4 could come up heads, or the 4 could come up tails. The 5 could come up heads, or the 5 could come up tails. The 6 could come up heads, or the 6 could come up tails. And now, each of these possible outcomes. So already we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 different ways that this could turn out, rolling a die and flipping a coin just once. And now each of these could also go heads or tails. And this one will either give me heads or tails. And this one will either give me heads or tails. Or this one, heads or tails. The 3 and then heads could come up heads or tails after that. The 4 could come up heads or tails. That was really messy. Do better than I did, please. In fact, I'm going to redraw. That was not good. And I'm hoping you get the idea and you can run ahead of me here and draw this whole thing out. Now, they call it a tree diagram because it goes forward and branches off like that. And what I want to show you is how to read it. So, for example, using my yellow highlighter here, I'm going to imagine I could roll a 3, and then flip a coin and it comes up heads, and then flip a coin and it comes up tails. That would be following just one chain of this. And so that would be roll a 3, flip heads, and flip tails. I could use my green highlighter and show a different example. What if I rolled a 5, then flipped a coin and got tails, then flipped a coin and got tails again? So roll a 5, flip tails, and flip tails again. And here are all these outcomes. And in theory, if the coin is fair and if the die is fair, all of these should be equally likely. So, and then flip a coin, and then flip a coin. How many ways can this be done? Well, we can actually just count these. That's the nice thing. So I could say 1, 2, 3, 4, 5, 6, 7, 8. You don't actually have to write the numbers, of course. I'm just doing it so that we can all count together and not lose count. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So there's 24 different chains I can follow. So there's 24 different outcomes. The 24 possible different outcomes. From rolling one die, then flipping 2 coins. 24 different ways it can come out. And from that, we can start to do theoretical probabilities using the tree. For example, roll a 3 and get tails on at least 1 coin. Well, we're going to look for rolling a 3 and tails at least once. So if we roll a 3, well, that's limiting us to this chain, to the yellow chain. And then we could either get tails on the first, and then it doesn't matter what happens after that. The second roll is irrelevant because we've already got tails. Or if we get heads on the first, it's still possible because we could get tails on the second. In fact, give me a moment. I'm going to erase the highlighter here. In the process, I may have to redraw some of this. That's okay. It'll be time well spent. So yeah, if we look at this, if we roll a 3, we can either get tails, and then either of these works, heads or tails. So far we could do 3 tails heads, 3 tails tails, or we could go up here and roll heads on the first, and as long as we roll tails on the second, we're okay. So there's 3 of these that work. 3 of these that work. We can go 3 heads and then tails. That's the first one. That works because we rolled a 3 and we get tails. We can do 3 and then tails and then heads. That's okay because we still have a 3 and tails. And we can do 3 and tails because it doesn't tell us we can't have 2 tails. It just says at least 1. So those are the 3 possible outcomes. So there's 3 ways to do that. And from there, we're going to come back to yesterday's lesson. If there's 3 ways to do that, what is the theoretical probability of doing it? Well, remember we said probability from yesterday's note and the day before is just the outcomes you're interested in divided by all of the possible outcomes. So the outcome we want to actually study, the one that we actually want to see, divided by all the outcomes that are possible. So in this case, the probability would be the 3 ways that that can happen. 3 heads and then tails, 3 tails and then heads, 3 tails and then tails. And maybe I'll put that here. 3 to heads to tails, 3 to tails to heads, and 3 to tails to tails. So there's 3 ways that we can do that, and there were 24 possible outcomes because there's 24 unique trees here. Remember, we just counted down that last row and it shows us all the possible branches. So this is the 3 ways to get a 3 and 1 or more tails. And the 24 possible combinations, possible outcomes. And 3 divided by 24 is not the nicest fraction I've ever seen, because we can definitely reduce it. So we could say this probability is 1 out of every 8. Hopefully we're all shouting. And I like that as an answer. That's a good answer. If we prefer it as a decimal, we can put that into our calculator. Right here I can say 1 divided by 8 equals, that's what I could say if it wanted to do it. Well, anyway, I'm going to let you do it on your calculator. And it is 0.125. And if we want to, we could express that as a percent, and it would be, good job, Brody, thank you, 12.5%. I'm going to assume Brody answered that. If Brody's absent, then I'm going to assume Deanna answered it. Good job. All right, we can ask more questions. You can pause this if you want and try the next 2 questions. How many ways can you get the coin heads up twice in a row? Well, if we look, the first branch after the 1, we can get heads followed by heads. And then no other branch in the first one does that. And if you look, the second is the same. If we roll a 2, there's only one way to get heads then heads. A 3, heads and then heads. 4, heads and heads. 5, heads and heads. 6, heads and heads. So for each of the original dice rolls, there's only one way to get heads and then heads after that. It should be 6. And if that doesn't make sense to you, let's slow down and talk about it. We can get a 1 followed by heads, followed by heads. 2, heads and then heads. 3, heads and then heads. 4, heads followed by heads. 5, and 6. Followed by heads, followed by heads. So there's 6 possible ways to do that. So I'm going to put those. Okay. So again, if we know that, what then is the experimental probability? Well, we said probability is just what? Thank you, Christopher Fowler. That's right. It is the ways that we can do the thing we want to do divided by all the possible outcomes. So in this case, how many ways could we get heads up twice in a row? Well, there were 6 ways to do that. What are all the possible outcomes? 24. And this, of course, reduces to a nicer fraction. What do we have there? Ali is screaming at me, 1/4. And now Tristan's saying, Mr. Orlando, I can make that decimal. And I'm saying, okay, go. And he says it's 0.25. And that, of course, leaves Jade who may or may not actually be registered in this class, to say that that is 25%. So again, we can always express a probability as a fraction, as a decimal, or as a percent. They all make sense. They all have real meaning. On the back, we'll do one more example. And if you want, you can pause this video and try and do it yourself. I think that's a good idea. And then once we've done that, I can follow along. So we're looking at pizza place, and the first thing they give you is a choice of size, followed by a choice of cheese, followed by a choice of toppings. And it's a good idea when you're drawing a tree diagram like this sometimes to sort of sketch it out like this. I like to sort of use light, faint lines and just divide it like that, just so I have a sense of where I'm going. And we have, in this case, three possible sizes: small, medium, and large. So I'm also going to kind of know that my first one's size, 3. And I show you this just to show, unlike last time, if I'm careful, I don't have to have the space become super awkward. I can use my space well. So the options for size are small, medium, or large. And then my cheese options are regular or extra. So I'm going to have this small pizza, and I can get a small with regular cheese, or I can get a small with extra cheese. I can also get a medium with regular cheese, or I can get a medium with extra cheese. And I can get a large with regular cheese or with extra cheese. And that brings us to toppings. We have vegetarian, pepperoni, or meat lovers. It's going to be messy, but we can do it. For the regular, I can do vegetarian, pepperoni, or meat lovers. And for that small with extra cheese, I can do vegetarian, pepperoni, or meat lovers. I should not have spread those out like that there. I didn't like that, sorry. And then for the medium pizza with regular cheese, I can do vegetarian, pepperoni, or meat lovers. And for the medium pizza with extra cheese, I can do vegetarian, pepperoni, or meat lovers. And I can repeat the same trick here. I can get a large pizza with regular cheese, and there I have 3 choices: vegetarian, pepperoni, or meat lovers. And the large pizza with extra cheese can also be a vegetarian, large pizza with extra cheese, a pepperoni pizza, large with extra cheese, or a meat lovers pizza, large with extra cheese. And those are all the possible combinations. So how many different combinations are possible? Well, again, it's as easy as going through and just counting them. So 1, 2, 3. So we're counting by 3s, right? Each of those final groups is 3. So 3, 6, 9, 12, 15, 18. There are 18 possible combinations. And hopefully you got that on your own, but if not, that's okay. We're going to get lots of practice, lots and lots of practice. Let's look at the questions here. How many different pizza combinations have extra cheese? We can start with a small, get extra cheese, and that doesn't matter what our final toppings are. That branch gives us 3 options. And I could get a medium. As long as I get extra cheese, in this case, toppings don't matter again. So that's 3 more possibilities. Or I could get a large pizza. And again, as long as I get extra cheese, the toppings don't matter for this question. So how many of these branches are highlighted? 1, 2, 3, 4, 5, 6, 7, 8, 9. So nine of the possible combinations have extra cheese. All right, let's start fresh here. And this question is, how many pizza combinations do not have meat on them? Not have any meat. Well, in this case, I would almost say this. That since it's not have any meat, let's just get rid of all the meat ones here. So meat isn't anything to do with size. It's not anything to do with cheese. So we're just looking at the last toppings here, and I can get rid of that one. I can get rid of that one. Oh, and that one, and that one, and that one. So how many have meat? 1, 2, 3, 4, 5, 6 of the combinations have meat. So 6 combinations have meat. Oh, any meat. You know, I made this question. Let's try this again. Because, of course, when I say any meat, that includes if we are talking about, if we're talking about a pepperoni pizza. So let's look at the ones that have no meat on them at all. And that is just the vegetarians. That vegetarian pizza, that vegetarian pizza, that vegetarian pizza, that vegetarian pizza, that one, and that one. So pepperoni has meat. Stupid Orlando. Obviously the meat lovers has meat, but the vegetarians don't. And there's 1, 2, 3, 4, 5, 6 possible vegetarian pizzas. There are 6 combinations with no meat. And we could list them if we wanted to. You could have a small pizza with regular cheese, vegetarian. A small pizza with extra cheese, vegetarian. A medium pizza with regular cheese, vegetarian. A medium pizza with extra cheese, vegetarian. A large pizza with regular cheese and vegetarian. A large pizza with extra cheese, that's vegetarian. I didn't ask for this. You don't have to list them, but just to show how we would read the chain. I could say small, regular, vegetarian. Follow along like that. So I could say small pizza, regular, vegetarian, small pizza, extra cheese, vegetarian. We could do a medium regular, it's vegetarian. But I could also do medium extra cheese, it's vegetarian. And I could do a large pizza that's regular and vegetarian. And I could also do a large pizza with extra cheese that's vegetarian. So those are the 6 possible vegetarian pizzas. And that's the idea with tree diagrams. They can be a really, really helpful way to come up with all the possible combinations for something. Now, full disclosure, they can also be, as you can see, a little ungainly. They can get a little complicated and a little big. So they're not always useful. But for a certain type of question, they really are the best way to approach it. So for the rest of today, you're going to be working on an assignment. And for that assignment, some of those questions will work really well with tree diagrams. Have a great day, guys. I miss you. But it's good to know you're in good hands, and I will see you soon. How do I turn this off? There we are.